The proportion is considered a measure of center when dealing with a variable that has a binary outcome. The proportion is usually defined as the number of observations within a process or population that meet a certain criteria, divided by the total number of objects assessed. Just like with the mean, we can estimate the proportion based on a sample. The natural statistic for estimating pi is given on the slide. This is just the sample proportion. It is determined by looking at the number of objects that meet the requirement divided by the sample size. Inference on a proportion is based on a random sample of size n selected from the population. Let's look at some details. Since pi is a proportion, we know that it can take on any value between 0 and 1. Just as what we saw with the mean, the sample proportion will change from sample to sample. As an example, let's assume that a sample is drawn of size 5. Usually we utilize a proportion as the measure of center when the data are binary. In other words, when there are only two possible outcomes. We will set one of the outcomes as a success, denoted by S, and the other as a failure, denoted by F. The success is usually defined as the outcome of interest. If the variable is considered capital X, then a success yields x equal to 1, and a failure yields x equal to 0. So based on the example given in the slide, we have 3 successes and 2 failures. This means that the sample proportion will be 3 out of 5, or 0.6. Just as with the sample mean, we get a distribution for the sample proportion. This distribution is centered at pi. The properties of the sampling distribution are given in the slide. As long as both criteria are met, we get the mean and variance of the sampling distribution as given on the slide. We will use this information to create a test statistic in order to test hypotheses and create confidence intervals for pi. Let's first look at the test statistic. Based on the properties of the sampling distribution, we define the probability statement as is in the slide. Then we can find the acceptance region based on the probability statement. Now let's find the interval. This equation is difficult to solve for pi since it is in the numerator and denominator. After substituting p in for pi in the variance and rearranging everything, we get the equation in the slide for the confidence interval for pi. Let's do an example. Here is a binomial experiment with 25 successes out of 100 trials. Let's determine the confidence interval. The first thing we need to do is see if we are meeting the criteria for our large sample approximation. Since both n times p and n times 1 minus p are greater than 10, we can assume that the sampling distribution for p is approximately normal. Now we will use the equations for the large sample interval. We interpret the interval as we are 95% confident that the true proportion of a certain type of failure is between 0.1651 and 0.3349. Now let's create a hypothesis test for pi. Recall that pi is a measure of center like the mean. This means that we will build the test statistic and hypotheses in the same manner. Let's first look at the test statistic. Since the sampling distribution comes from a normal distribution, we can create the test statistic based on the z-test. This test statistic for this situation is given in the slide. Notice that it is very similar to the test statistic for the mean. We use this test statistic to test the null hypothesis that pi is equal to some specific value, pi naught. Let's look at our assumptions. At this point, we will adjust the assumption. For the confidence interval, we did not have an idea about pi, so we use the sample proportion. Now when we run a hypothesis test, we make an assumption about pi and assume that it's true. Now we can use it directly in the assumption. The new assumption is given in the slide. Let's do an example. Now let's create a hypothesis test for pi. Recall that pi is a measure of center like the mean. This means that we will build the test statistic and hypotheses in the same manner. Let's first look at the test statistic. Here are the null and alternative hypotheses. Now let's look at the assumptions. Since both are greater than or equal to 10, we can assume that the assumption is met. Here is the calculation for the test statistic. The p-value in this case is 0.1587, and the critical point is negative 1.645. Now, since the p-value 0.1587 is greater than alpha, which is 0.05, we will fail to reject the null hypothesis. Since the test statistic, which is -1, is greater than the critical point, which is -1.645, we will fail to reject the null hypothesis. We can conclude that since 0.1578 is greater than 0.05, we will fail to reject the null hypothesis, and we can conclude that the process is not running up to expectations.